So I was about to start. I can hear some background noises. So if you have anything, you just then you can turn on your mic. Otherwise, please turn it off. Can you see my screen? I guess yes. Hello, am I audible?
Yeah,
Yeah. So basically today, I think it will take 1.5 hours to teach you the Hartree-Fock coding. So this is the just a minute. Yes. So this is the GitHub link where actually we'll follow this. This is the Hartree-Fock self-consistent procedure. So this is for the C++ language. So you can code it in any language. For the simplicity, will we actually code in Python. So these are the steps that we are going to follow. So there are we can see around 6 to 10 steps. So after the convergence, so there will be iterations. So we'll go step by step. If you have any doubt, just let me know. And uh, yeah, okay, just give me yeah, it's fine. So as you said, you are a little bit familiar with Python, right?
yes, yes.
Okay.
But like, I've never coded any computational chemistry algorithm on.
Sorry.
I've like never coded any computational chemistry algorithm on Python though.
Yeah. Okay. It's fine. Actually, I'll explain everything. If you know the basic Python, then I think it will be fine. So we are importing the NumPy as a package as import NumPy and time. So in certain portion, if we want to check the timing, we can use that module. So these are just two import statement. Now, so what is the step one? So, so first thing, you can open a Google Colab, okay, and there you can create a. So there is this. You can create a like Python project there. And so here you can see in this, there are the files option, right? So here actually, so you can see here that they have provided some of the data like this ENUC, yeah, like nuclear energy dot dat file, and the file contents looks like this. So they have given the nuclear repulsion energy in terms of atomic unit. So it is provided, and here are several things like overlap integral. You can see the kinetic energy and the integrals that you need. So they have provided those. So so you can download this from here. So I'll just give you an example. So if you click the overlap here, you can see this is the file, and here you have the download button. So if you just download it, it will be downloaded and you can use that. So I have already downloaded it. So let's
Should
upload.
I like open a Google Colab right now?
If you want, that is fine, or you can. I think I'll suggest you have a look first. You watch, then you will have the recording also. Then after that, you try it yourself. I think that would be better because within the 2 hours timing, I don't think so. If you do simultaneously, we'll be able to complete. So I'll show you first. If you have any questions, any doubt regarding the coding, you just let me know. And then after the class is over, or if you have any spare time or something, if you are interested, you can code it yourself, like without seeing my code. I think that would be even better. Always try to code on yourself, because then like you will face many debug like many bugs there, many error, and you actually learn from the error the most, not just by seeing the code. So you try by yourself when you are free. So yes, so there are different basis set. They have calculators like DG with polarization basis set, and STO3G. So I'll just show you quickly. So below here, you can see this portion. They have given the STO3G water, the DZ water, DZP water, and the files are given all here. And from there, you can do the check. So we'll first start with the STO3G.
Can you once explain the last part you said? I could not get.
Okay, so here what so this overlap integral S and the kinetic energy integral T and your V, like the potential sorry, the attraction integral and the force center two electron integrals, they are different in different basis sets, right? Because your basis set changes, and so this number and the number of content that will change. So they have given those files here, like STO3G, DZ water, and DZ with polarization basis set. So this is the largest basis set they have used, and they have provided the data. So we'll start with the STO3G. So the code will be same. You just have to replace the files there. So I'll show you. Okay.
So
So
the data are the overlap integrals.
yes. So for example, let's say this overlap is. So you can see this is the overlap integral data. So this is the content of the file. So this has been pre-calculated. So in this uh, in this tutorial, I am just going to complete you this project, like how you can complete this project given here, provided you all the integrals they have given. So there are many softwares there, they actually calculate these integrals. For example, I think you might be aware of PySCF, or there are libint, many software they actually calculate the integrals, and that is a very tedious job. Even I don't know how to calculate it, but I know that that can be calculated from different software. So my goal is to complete the project, like to code all the other parts that is required. So you are only given this data here. For example, this is the your nuclear repulsion. So you just have to read the number from the file. So your this is fine. Then this is your overlap integral. So you can see there are three columns here. So this is your numbering. So this is just a serial number, but this is your file. So what does that mean? Though I'll explain again. But as you question, so let me answer. So this means that your this is the overlap integral between your atomic orbital 1 and atomic orbital 1, which is 1. And this is the overlap integral between your atomic orbital 2 and atomic orbital 1. So the you are when you do a basis set, so that is your you are in a AO basis, right? So you take the linear combination of AO and you form the molecular orbital. That is your LCAOMO. So you know the Ruthan equation, right? In the Ruthan equation, you take the linear combination of the basis set, and there you need the integrals, this S mu nu, this integral.
Yes.
So these are provided here. So we just have to we have to read it very carefully and smartly. That I'll show you. When I'll read all this file, I'll show you. So just I want to mention that I am first doing it for the STO3G cases, and I have downloaded already the files here. So I just need to upload it in the this project here. So This is the file section. You go to this file section and you upload the files here. So getting uploaded.
Can you once again tell what those values were like? Just you opened the table, I think.
So these values is the so this 1 1 or 2 1 3 2. This is the numbering of your atomic. So for example, chi 1, chi 2. So these are your different atomic orbitals. And when you take the overlap integral, so this is their value. For example, this is your overlap integral.
Are they from
And
the same molecule or same atoms?
sorry,
They're for the same like atoms. I'm saying. Like, are these all for water or something?
yes, this is for water.
Okay.
So they have provided the geometry here. So this is for water, and this is the geometry in Cartesian coordinate they have provided. And within this geometry, this is the overlap integral they have given.
So these are the coordinates of the three atoms.
Three atoms.
So why there are four coordinates or six? Oh, okay, got it. There's six.
So this is the number of atoms there, and this 811 is your oxygen, hydrogen, and we don't need this file actually. Uh, but yeah,
But why are there eight values?
where?
There are like eight.
So
I
no,
think there are nine values or
so
12 values.
actually, so this eight corresponds to your atomic number of oxygen, and this one corresponds to the atomic number of hydrogen, and this one for your hydrogen. This is a different way of representation. So usually they write oxygen HH, and this is your XYZ coordinate. Is it clear?
Yeah, yeah.
No. So so this is the overlap integral they have given here. Yes. So it is uploaded. So uh, let's define a variable first. File path. This is the content. So now why I have told you that why it is defined like this, because here if you click any file and you copy the path and you paste it here, so you can see this is slash content slash s dot dat. So I will actually take different data file from here. So I am just defining a file path which is like your within the string, that is slash content content. Yeah, sorry, slash slash. So this is your file path. This is just a variable, nothing to worry about. Okay.
Why do you name it content?
Huh?
Content here is
So here actually in Google this Colab, where I have uploaded the files, so it's just like a folder name. So they have given the folder name as content by default.
okay.
So in your computer you can create different folders, like so here you can also create different folders, but by default where I have uploaded the files, that folder name is content. Okay. Now let's read the. So here I have the nuclear energy data. So let's go step by step. So the step one is to calculate the nuclear repulsion energy. Yeah, step one, and nuclear repulsion energy. So how will we, so we can use with open. Here you have to provide the file path plus and the data file name. So that is there in the U nuclear, like nuclear energy dot data file. You have to read it in read mode with open as air. So this is the syntax how we'll open a file, right? So now the lines f dot read lines. So this will actually read the files and the, these lines is basically a list. So I'll show you how these lines looks like. See, this is a file. This is a list, and there is a and this is a string. But I need the number, right? I cannot work with the string. So what I have to do? I have to write
So there is only one value in the
yes.
lines.
So here you can see this is the nuclear
Okay.
repulsion energy, right? That is only one. So it's a repulsion energy, and that has to be only one
Mm,
content.
mm.
That part what I have just read. And so your E nuclear will be so these lines is a list. So you have to
What is
just
with open means?
with open it's a syntax how you'll open a file.
Okay.
So this is a just syntax. There is no logic behind like the why I'm writing like this. It's a Python syntax and I have to follow it. Otherwise you will get error. There are different ways, but this is one of the way you can read a file. So and then you have to take the first. So these lines here, these lines is a list, right? I have already printed here. So these lines is a list. So I need the first item, and so you can do a which is called a strip. So what it does is now see this is a number, and that's this strip. What actually does is that so when we printed the lines, I'll show you once. So when I printed the lines, you can see there is a like different like many white spaces are there. So we don't need it. So with the this help of this dot strip, you can actually get rid of all the white spaces, and you will only get the numbers. And that's what it is used for. Now you may think that okay, now my job is done, but actually, if you print the type of the this variable. So I have defined a variable here, right? E underscore NUC, the nuclear repulsion energy. So it must be a float, but here you can see it's a string. So with the string, we cannot do any multiplication, addition, and anything. So that is very simple. You just do a float. You convert the string to a float. And now see, this is a float. So now you can do any addition and other stuff here. Okay, so now our job is done. So print nuclear repulsion energy, repulsion energy. Let's see. Yes, so the first step is done, and this is our nuclear repulsion energy. Now, what is the second step? The second step is that you have to read the all the one electron integrals. Again, the same procedure will follow. So So I have already explained that what is this overlap integrals looks like. So these are your atomic numbers and see what are the things are written here. Note that, uh, can you give me a second, please? Just 1 minute. Okay. Sorry. Uh, so so it is written here that note that only one electron integrals and that are provided the permutationally unique integrals. So do you understand the meaning of this line?
Uh, so does this mean like the only the Coulombic part is given?
No,
Also
actually. So
only the
now we, yeah, tell
repulsion
me.
uh, only the repulsion. Okay. Only the Coulombic part is given.
No, for any like for your overlap integrals also. For your overlap integrals, they have only provided the unique indices only. For example, if you look at
Okay, got
carefully,
it.
so actually they have only provided, for example, 1 1 or 2 1, for example, 2 1, but they haven't provided the 1 2
One, two.
integrals. So,
Okay.
and so as they are real orbitals, so we can infer from here is that 2 1 will be same as your 1 2.
One, two. Yeah.
So you have to write it very carefully that your 7 1 or 7 2 all the overlap integrals, so you have to take the 2 7 from here or 3 7
Okay.
from this value. So that's what is the meaning of this line. And the
Okay.
similarly for all the one electron integral, like their
Okay.
kinetic energy, nuclear attraction integral, they have only provided the unique integrals, right? And another important thing is that here the indices that start from 1, right?
Hmm.
1 1 2 1 like this. But
Hmm.
as you are coding in Python, it's a very important thing to note that your indices will start from 0. So we have to, so this 1 1 actually in Python means 0 0, and two
Okay.
ones means 1 0. So we have to convert it carefully, and we'll do it actually. So those who have joined lately, I just want to mention you that uh, we are uh, we are going to solve this project given by the Crawford group, and we have started reading the nuclear repulsion energy, and we have read it already here. We have read the nuclear repulsion energy from here, and now we will read all the one electron integrals provided there. So let's just code it. So so this the overlap integral. So we can also read it like this: np dot load txt. So it will, so now file path plus, and what is the your overlap integral? It's a s dot a dat file, right? And so just for your convenience, let me print the how does it look like this s, and as you can see, it has already taken all the values, and it's a, so it has taken uh, the this whole text as a array. So I hope you know what is array is. Array is nothing but a, it can be matrix, it can be three-dimensional, it can be four-dimensional. So array is a uh, you know certain ordering of your numbers. So it can be matrix for your simplicity, it can be matrix, 3D matrix, 4D matrix like this. So this print, you can see there's a array, and you can also print what is the type of this S. So I'm just printing the type of S. You can see it's a numpy.nd array. It's a numpy array actually. Okay. So similarly, let's read the other files. So what are the other files? Uh, the other files are your kinetic energy and nuclear attraction integrals, right? So T is equal to this, and V is equal to, even with this numpy like np dot load text, you have you could have done this also, but here I'll show different possibilities so that you'll have a larger varieties of option. Okay.
So each ST and V this they're storing different integral values.
Yes, I'll replace with t dot that. Yes. And now, yeah, tell me.
Like, how is Python doing this? Like, uh, it is sequentially getting like so s represents to 0, comma 0.
Yeah, I know. Here I have just read the file. I haven't done the processing. The processing file part I'll do it. So
So,
if you print the S here, or let's print the T here. So now if you print the T, you can see that it's a matrix. It's a matrix is a two-dimensional which has a number of rows and three columns. So the first two columns are your the indices of your actually the atomic integrals. So here it is 1, 1, 2, 1, 2, 2, but I don't want in this order. I want in 0, 0, and also here the unique values are given. So I have to load all the values. So if I don't have the values for, let's say, 1, 3, because only 3, 1 is given. So I have to write in such a way that here 3, 1 is 0. Here the
okay, so
3,
the
1 is
indices
0.
are only given.
No, indices plus their value. This is your kinetic integrals value. That is also given, right? I have
Okay.
already shown you.
Why is the indices coming like 2.00 e?
It's just, sorry.
Like, it's coming in terms of e. The indices are.
Okay, so it's just the way the NumPy is loading it. So I'll
Okay.
I'll just show you that you can convert to this integer. So here you can see I have converted into float. So in the latter part when I'll actually process the data, so there you can see that I will actually process it with help of integer. So let's open the kinetic energy file how they have written here. Yes, this is the way they have written 1 1. And so actually how the Python is doing actually. So here you can see the numbers are in float, right? So they are also like converting this 1 1 and 2 1 into float. So there is a way that you can do it. You can just print t dot d type. So it actually print the data type of your matrix that you got. These are irrelevant, but so you can see it's a float. But we want some integer, and I'll show you. Uh, I don't know whether I'll be able to complete it, but yeah, let's try. Okay, so we are done now. So first thing to note that this is in the your like spin adapted version, like this is your RHF. Now how will you, so there are many atomic orbitals given here, but what is the basis set dimension? Like I think you have already like Professor Pal has already taught you like how to calculate the basis set dimension, but it can be actually calculated from this file. So for example, you can see what is the largest number here, 7 7, right? So that means only 7 atomic orbitals are given. And in water, how many electrons are there? 10 electrons. So each MO will be filled by 2 electron. So there will be 5 occupied and 2 unoccupied. And the total number of AO is 7. So you have 7 atomic orbital. If you take the linear combination of 7 atomic orbital, you will have 7 molecular orbital. Right? Is this part clear? Or I can show you another file. For example, this d zeta or double zeta function. If you open any file like overlap integral, so see here the maximum number is 14. That means the number of total AOs is 14. Like, is there any doubt? Like you need to calculate the how many total atomic orbitals are there, and that can be actually easily
Okay.
seen from the file. That here you have only 14 atomic orbitals.
But the number of electrons are, I think,
Yes, that is true, right? The number of electrons is 10. But so when you solve a Hartree-Fock equation,
yeah.
you get many orbitals and you take only lowest energy orbitals and you form the
Yeah.
one single determinant. That is the
Yeah.
goal. And the other orbitals, actually, we call it as virtual orbitals. I think it is like well known, right? So what am trying to convey here is that the total number of AOs is 14 here for the double zeta cases. And for the STO3G that we are dealing with, the total number of total number of AOs is 7. Because if you had 8 or 9 AOs orbitals, so where are those integrals? So those integrals are not there. So that means only 7 number of AOs are here. So we'll fetch the number and how to fetch the number. So you have already loaded the data. So let's call it as number of molecular orbital or NMO. And how will you fetch the number? So so you can actually np dot, or let's go step by step. So in the first column, so here you have 3 columns, right? The first 2 columns are your AO indices, and the third column is your value. So I need the maximum number that is present in my first column. So then I'll get my total AO number. So then how could we do it? So let's do S, and you take all the values from your first column, right? Or how did I do it? NP dot sort. Yes, from your first column. We have taken all the data here, and let's print the NMO. So you can see here that all the numbers are actually printed here, but you need the largest number. So what you can do is you can sort it np. So there is a function np dot sort. This will sort from in the ascending order, like the lowest value will come first. I'll show you 1, 2, 2, 3, 3, and this like. So you need the largest number. So that means the last value you need it. And from the basic Python, you can calculate the last value as -1. If you put the index -1, it will calculate the last value, which is 7, right? But uh, it has to be integer, like the number of atomic orbitals has to be integer. There the 7.5 or 8.3 has no meaning, so it has to be integer. So let's convert it to integer. Yes, so see, this is the, so my total number is defined, that is your 7. Okay, any doubt in this syntax? Okay, so one quick note here. So I know my molecule is H2O, right? But when you are a general coder, so how can you calculate the number of electrons, right? So I'll just show you how can you calculate. So for example, when you are given a geometry file, for example here, if you have a oxygen, you can see here, and you have hydrogen 1 here and hydrogen 1 here. So that means the total number of electrons is 10 here. And if you are given a charge, for example, it's a +1 charge, that means 1 electron is not there. So what you will do, you will do a 10 minus 1, that is your 9 is your total number of electrons, right? So from the geometry file, you can actually calculate the total number of electron. But as for simplicity, I know I am dealing with the H2O molecule in its neutral state, so my total number of electron is 10. Okay, for example, if you have a methane molecule, so here the methane molecule is given. So from the geometry, again 6 1 1 1 1, that is 10 number of electrons. if so from the geometry you can calculate the total number of electrons and you can code it very easily, but here I am not going to do it. I'll just write the total number of occupied orbital is 5 because 10 electrons and 5 occupied orbital and other two will other any orbitals will be virtual. So then what is the number of virtual? N var is
The NMO minus M.
what is the?
Like NMO minus N, which
Yes, correct. NMO minus
by
NO.
2.
So no, here I'll just generally define that. Yes, so yes, here will be 2. So let's print total number of AOs. You print here NMO and occupied NO and virtual N var. Yes. So total number of AOs is 7, occupied is 5, and virtual is 2. And we are good to go. Okay. Now, okay. So our the first part is like the first step is done. The second step, we have read the file, but we haven't actually done all the permutations. Like we know the unique numbers. We have to do two things. We have to fill all the numbers from the permutation symmetry, and whatever the indexes start from 1, we have to convert in the zero-based indexing. And that is what we are going to do it here. So um, um, let's define a function, one electron.
Okay. So we are basically solving the Ruthan equation in the orthonormalized basis, right? Through like iterations.
Yes, we are going to solve the Ruthan equation here. That's what the project is. One electron data. So we need some argument, and I have given, so let's say unique data. We are provided with the unique data only, and you need a container. I'll come to I'll explain what is container. Right. So let's take the overlap integral at np.0. So I'm initializing a file. So what will be the shape of the your overlap integral? Can you tell me? The overlap integral is this S mu nu. So this is a two-dimensional matrix because it has two indices mu nu. So can you tell me what will be the in like what will the shape of this matrix? The T mu nu or V mu nu or your H core code Hamiltonian that we are going to build from here. What will the shape?
Can you repeat the question?
Yes. So you can see the first thing to note is that your one electron integral is a matrix. It's a two-dimensional matrix. Okay. So now can you tell me that what will be the shape of the matrix? I mean, how many number of columns or how many number of rows in the this overlap integral or kinetic energy integral or nuclear attraction integrals you expect? How many number of columns and rows?
6, 7, and 7 columns, 7 rows,
7 column.
7
Yes, that's correct actually. So you need to for generalize, what you will do? You will initialize a matrix filled with 0, which has a shape NMO, comma NMO. So this tells the Python you generate a array of shape NMO, comma NMO. That means NMO number of rows and NMO number of columns starting with 0. Right. Now we'll fill the values. So first we are initializing it. So again, the same goes for your T and attraction integrals, this. So you have defined the data, and this is your container. So here I am, what I am saying, I will pass this like zeros entry container to this function, and I will pass the unique data. What is my unique data? That is your small s, small t, and small v. I have read from the file. So that is their unique data. Now the container is the initialized array, and now I will fill the whole container from the unique data. That is my goal. Is my goal clear?
Yeah, so we will fill the matrices with the values basically.
Yes.
2D arrays. Okay.
Yes. Then we'll only deal with this container species only.
So container here is where is the input container?
Yes, so when will this is the I'm defining a function now in Python.
Oh, okay,
Now
okay, got it.
when I'll call, so when how I will call it, I'll just show you. If I say s equal to one electron data, one electron data. Now what unique data I will pass the s, and the container I will pass the s. Now is it clear? This I will do later, but I am just defining the function first. Right. If I run the code, it will throw me an error because nothing is like defined now. So let's do it. And here you have to be very clever enough. So let's let's write the function. So so how many number of rows are there? So unique data. So in unique data, how many number of rows are there, right? So here you can see 28. Like, so 28 numbers, so I need that. And why do I need that? I'll show you. So, and that you can do if you do uh, unique data, unique data dot shape, and if you take the only the first value, this is your, so unique data is a two-dimensional matrix. So when you take this dot shape, it actually prints the number of rows comma number of columns. So now if you take the first value that is given in this index, so then it will give you the what are the total number of rows. Because, and now why do I need this total number of rows? Because you will iterate over all the rows, right? So how will do the iteration? You know for loop, right? For I in range. If you have any doubt, uh,
Yes, here use your initial array. Unique data have you, so later will you, this unique data is basically just S, small t and B, right?
the data that I have read from the file.
So you have to like name those as unique data.
Huh?
You have to name those data as unique data, right? You have not named it yet.
I haven't named it yet. Means,
Like unique data, you have not created something called unique data variable here.
uh, so when you define a function, so here I am calling that my unique data. But as you can see from here, when I call the function, in place of this unique data,
Oh, got it.
I am passing the s, like small s, and in the container I am passing the capital S. So here my small s acts like a unique data here. So this is just a nomenclature. So you don't need to actually create the unique data if you define a function. Okay. Now I need all the numbers from here. For example, I have to read all the rows, like the first row, second row, third row. That's why I am iterating over all the rows. So for I in range rows, now what is the row value? I'll when I'll print it, it will be clear unique data I. So what does that mean? So this means I will iterate over all the rows, and this is the my row value. So I think I should create it somewhere here. Yes. So let's print row. So now you can see it has print all the rows like 111, because here if you open the file like overlap file, what is the first row? 1 1 and 1, right? And that's what it print here, 1 1 1. And then what is the second row? 2 1 0.2367. And so I can fetch all the like different rows from here, right? Now I have to do the manipulation only. So now you have to fill the data. So what is my atomic indices here? Your mu is int row 0 minus 1. Now why did I do this? See, you have to fill the mu new, right? This mu and new, and you are only given certain mu and new, like 2 3, like 3 2 or 4 2, like this. So the first value that is given by row third bracket 0, and that was in float, so I have converted into integer. Now that is in the one based indexing, but I have to create in the Python based indexing. That's why I have subtracted 1. So this is your mu, and what is your new? New is your the value of from the second column, right? Any problem here? Now I'll fill the data like this is your container, right? In the container, in the place of mu, comma new, what is the value of your overlap integral or anything that you are going to calculate? That is the third row element or third column. So that is 2. Now put value, and here you do the permutation. So let me write it and then I can explain. New mu. Now check it and let me know that if there is any doubt.
What is value row index 1
Okay. So let's check the how does the S mu new look like. Okay. So you have loaded the file. We have did it in here. We we have already loaded the file here. Right. Now, when I am reading this file, the first column actually tells you the indices of the mu, right? This mu new. So the
Yeah.
first indices your mu, and the second indices your new,
Yeah.
right? Similarly, this. So now here I am iterating over all the lines. Here for I in range rows, that means I am iterating from first row to last row, right? So in every iteration, I get this line, which I
Yeah.
have defined as row.
Yeah.
Okay. Now in this row, you have three values. The first value corresponds to the mu,
Yeah.
and that is
Okay. Okay.
given as row 0, but that is in the one based indexes, but I need in Python based indexes. That's why I have subtracted 1. So this is your mu, and again this is your new, all the second column, and that I have defined it as C row 1. So this is your new, and what is the value? Value is your the third column, right? So this is your third column. This is your value. Now what I did, I am filling the container. So the container is the initialized zero value. If you remember np.zeros, now I am filling the array. So mu new is value. This is given, but I know the new mu will be the same. So that's why I am switching the indices and placing the same value. Is this part clear?
Uh, so why container has two indices?
Huh?
Okay, a container has two indices because it's a two-dimensional array.
Yes, yes. You have already answered yourself, right? So here I am in the one electron integral. So still this is fine. When we are going to do with these two electron integrals, it's like these two electron integrals, it has four indices, and here the things will get even much complicated. So I want you to clarify all the doubts here, because if you know the two like 2D matrices, the 4D matrix will just be straightforward. So
Okay, and
so you have filled all the arrays. We'll check it now.
so
Let's
till now, whatever the code we have written, we have filled
we are
all the containers.
yes
We have
we are filling the containers. So I
so we
need
have got all the integral values
all
basically
the
in
integral
Z
values,
matrices.
and from this line. So this is the smartest move here. That
So why do we like we will get different return values for container new and container new?
sorry.
We will get different container values for new and new.
Yes. So it is iterating over all the rows, right? So
Oh,
it will go to the first row, then it will come to the second row, and from there one value it will fill two value, right? So it eventually it will come to this, it will come to this and this. Now let's do a
okay.
check. Let's check here. So so we have called the function here, one electron data, and we have passed the unique data, we have passed the container, and now it has already filled. Now let's print. So before printing, let me ask you this question. This 6 3, right? This 6 3 value, it should be here. How should I fetch the number here? Like this 6 3 value is 0.2684. How can I pass the indexes so I get the value? What should I pass here? What
Should it be like S
mu new, right?
okay
What will be the index to get the 6 3
S
value?
6 comma 3?
So let's pass 6 3, and let's see what is the print, which is 0.2097, but it is 0.2684.
Okay, so it should be 5 5 comma 2.
Yes, actually it's a
Okay.
Python based indexing. So it will be 5 2. Now see 0.2684. Now again, if you see, if you print 25, that was not there. In the file, there was no value as 36. Here you can see no value with starting as 36. But if you print it, They are the same value. So from here, you can
Yeah.
see you have loaded the structure carefully, right? Okay. So now we are done. The simple thing. Now let's fill the other thing, the kinetic energy and the potential energy part. So here it will be T, V, comma, V. Right? You have filled it. And what is the second job? You have to define the core Hamiltonian, H core. So H core is what? H core is T plus V. Just T plus V. And you are done the H core. So we are done up to the second part, the second step. Any doubts so far?
Here T nu nu is the okay, nuclear.
It's a just so the T mu nu is a matrix representation. It's a 2D matrix, and V is a 2D matrix, and you just take the sum and you get the H core mu, and that's what I did here.
So in the lectures we have not written the H code as T plus V. So it is the nuclear electron attraction plus nuclear electron repulsion.
No, no, no. H core is always no. I think in lecture also it is there. The H core is the um, one electron kinetic energy plus the electronic attraction integral. That is your H core. And the other parts is your Coulomb minus exchange. You go and check. So now we have to do the hardest part, that is your reading the two electron integrals. And let's do it. And here let's read it carefully, then we'll go to the coding. So let's first check the data file. So it's a four-dimensional matrix. So and it has a eightfold symmetry. And you can see in the data there are lots of number given. And again, the total AO is 7, just as the your overlap integral and the electronic kinetic energy integral and whatsoever. But they have provided only one type of integral, right? And only the permutationally unique integrals are given in the file. So, and this is the condition they have followed. So what we have to, we know this mu nu lambda sigma. And from this mu nu lambda sigma, we can generate this other seven combination. And the way we did it from the for the overlap integral and other one electron integral, we are going to do the same. But here it will not be twofold symmetry. There we had mu nu, we did just mu, and we are done with the filling of the all the container. But here we are given only one value, and we need all the other seven values from here. So for example, this is the value. For example, um, if you see the 6131, so there is in the file you can go and check, there will be no value as 1631. There will be no value given there which is 1631, or you can say 316, 3161. We can generate it from here, and I'll show you. Is the problem clear?
Yeah.
Okay. Okay, so if it's clear, let's load the value. Again, we'll do the same. So the electron repulsion integral will say ERI So electron repulsion integral np.log text dot file path, and what is the file name? Your ad dot data. So you have loaded the file. Now again you have to define a function. Define two electron data, and you need unique data, comma, container. Okay. Now tell me what will be the shape, like the way you generated these np dot zeros. How will you generate
Just
the,
there will be four indices. Rest will be same.
so how will you generate it? It will be the,
P dot zero, no comma, and no comma.
here we,
There will be four coordinates basically.
so nmo comma nmo comma nmo comma nmo, right? So let's define at initial int. So that means electron repulsion integral initial data. Okay, so we have defined the data. So in the container, we'll pass this as argument, and the unique data will pass this, right? Now let's write the thing. Okay, so again the same thing. Rows. This is the again the shape, the total. It's a 4 dimension. So what is the file? So this is the file, right? So now can you tell me what is the? It's a matrix or it's a high dimensional tensor?
Mm. Tensor.
Yeah, you are right that the way you have defined NMO, comma NMO, comma NMO, that is a tensor. That is a 4 dimensional matrix. But the file they have given, it's a matrix. See,
Yeah, two dimensional.
it's a 2 dimensional matrix. It has a 1, 2, 3, 4, 5 columns and 228 number of rows. So the file they have given, that is a matrix, but from this 2 dimensional matrix, you will generate a 4 dimensional tensor. That is NMO, comma NMO, comma NMO, comma NMO.
Yeah, yeah.
Okay. So the first thing, the first column gives you mu, and the second column is nu,
New.
the third is lambda, fourth is sigma. Okay. And the fifth is the value of the integral. Is that clear?
Yeah.
Okay. So let's define mu as, let's copy it from here.
So should we change the definition of PRI?
Here,
Should it still be a new comma?
yes, the container you will fill, that will be 4 dimensional matrix. But the thing you are passing, that is a 2 dimensional matrix. So what we'll eventually do, so will Aries equal to, we'll call the function to electron data. Now you have to, what is the, how did you write here? You need the unique data, comma, container. What is your unique data? Your unique data is ARI int, and the
Mm.
container is ARIS, electron repulsion integers. Is this clear?
Mm.
Okay. Now do the processing here. You have defined a mu new, then you have to define lambda. So you cannot just write lambda because lambda is a already defined in function, already defined in Python. So I am just giving an underscore, lambda
Yeah.
underscore. So lambda is a function, yeah, lambda, and you have sigma. Okay, so the first is mu new, then this is your second. This is sorry, this is your fourth,
Right.
and you have the value. Value is 4. Is it clear?
Yeah.
Now I'll do the, it will take some time. I had already written the code before, so I'll just copy paste, but I'll explain. I could have just explained this code which I have already written, but I want to, like, if I show you all the code, you will be bombarded with lot of lines and you will not be able to focus. So I'm just going step by step. So that is the motto. So now this is the eightfold symmetry. Now
Uh,
check this.
can we like if we don't subtract -1,
Mhm.
so can we like avoid the Python indexing change later also? Like later we have to like while calling the function we reduced -1 in the input values. So if here if we don't reduce the -1, then there also we don't need to reduce it.
Yes, so the problem is if you don't do it here, so what you will do, so let's say, for example, let's explain with this one electron data. So
Hmm.
here I have subtracted one here and subtracted one here. So now let's say that you didn't do it here. So let's take an example where your mu is 5 and nu is 4,
Hmm.
right? And if you subtracted it, so your mu becomes 4 and your nu becomes 3. But if you
Yeah.
don't do it, actually in the container, it it starts from 0011. So
Hmm.
if you fill in a different way, like if you don't subtract it, it will fill the other indices which you are
Zero.
not intend to do.
Okay.
And that is the problem. So when you have a data, you have to first do so if you are coding in Python, you have to do the zero weight indexing. But if I have coded in Fortran this, you didn't have to do anything because in Fortran you start from one.
Okay.
Okay, so this is just a convention that we have to follow. There is no other option. Okay, so I have fetched the value. Now let's see if you have mu nu lambda sigma. So I have filled the mu nu lambda sigma as the value in the container, which is a four-dimensional matrix. That's why it has four indices, mu nu lambda sigma. Now from this mu nu lambda sigma, what you can get? Nu mu lambda sigma. So I think you remember, right? The one-two switching and the permutation switching we have already discussed in one class.
Hmm.
So this is the 8-base indexing. So in the same way, I have defined it nu mu lambda sigma, mu nu lambda sigma, like all the 8 values. Do you have any problem up to this? And again, we have to return the
Yeah.
container, return the container. Okay. Now let's do a quick check that we have done it correct or not. Print Aries. What is the value that you want to print? Let's take any value. 6232, right? Let's print this value. So how do I need to print? 5121, right? 5121. What is the value? Uh, we get we got an error. Row is not defined. Okay, okay. So the row was not defined. Again, we got LMB. Yes. So there was some mismatch in the naming. So 0.03377. 0.03377. Now we also expect if we do a switching, like let's say, can you tell me the index, the similar, it will have the permutation symmetry? What do you want me to print? Let's see. I think 2 1 5 1. They should have the
One
same.
five one two
Okay, you tell me. 1 5
one two.
1 5 1 2. Yes, it will have the same value also.
It's a method to actually check our
Hmm?
symmetry also. Also a method to check our symmetry.
Yes, and it has to be followed, and that's what we have done here. So we
5112, can you check?
5
112.
5 1 1 2 5 1 1 2. Yes, it will also come out to be same. But let's check this one, which will not come out to be same. I think 5
5211.
2 1 1, because and see this is different. Yes, so we hope we are good to go. And now, yes. So our step 3 is done. Now it's the starting of the Rutherford equation. Build the orthogonalization matrix. Okay. So they are asking me to diagonalize the overlap matrices. So the matrices we got it here, yes, we need to diagonalize. And in one of the classes, I have shown you how to diagonalize a matrix. And do you remember? Lambda S. So I'm just giving the same nomenclature they have given here. Lambda S and LS. So how do we, if you want to diagonalize it, you can use the numpy dot linear algebra dot eig or eigh, but we know that our matrix S is Hermitian because it is symmetric. So we'll use the EIGH and we'll pass the matrix like S.
So this is the
This S matrices we have to diagonalize. Yes, tell me.
okay. This is the S, and we also have to find the F, I guess, from S.
Like Fock
Yeah.
matrix.
Yeah.
Yes, we'll do it here in the step 5.
I think the notations are a bit different.
Yes, it might be right, but the logic is will be same. Whatever you have learned in that course, the Rutherford equation, it follows the exactly. This is your Laudin's uh, the Laudin's way how you actually define the Fock matrix, and there were different partitioning available, right? So you are using the S to the power. If you remember the X matrix there in the course, and that is your S to the power minus half here. So before coding this, you check with your note and this project description. And so I'll just do one thing. I will copy paste the link in the chat. So maybe check it out from here. Okay. So we have diagonalized the matrices. Now what we have to do? Now build the symmetric orthogonalization matrix. So now we have to get the lambda to the power minus half. We have got the lambda s. So let's it's what is the lambda s? Let me show you. Lambda s. See, it's a list, and which are the 7 number 1, 2, 3, 4, 5, 6, 7. Because your S matrix is a 7 by 7 matrix. If you diagonalize this, it will have like it will have in the diagonal will have 7 elements, right? Because 7 any n by n matrix has n number of eigenvalues. So 7 by 7 matrix means 7 number of eigenvalues. Now you have to take the minus half of each of these element, right?
I wonder like what is LS?
Ls is the eigenvector of these eigenvalues. So if you remember one of the
Which
classes,
eigenvalue?
so if you remember one of the classes that if you diagonalize a matrix, it will have a so basically so any matrix A and it will have AX and X omega, and this is your eigenvectors. And if you remember that these X eigenvectors were the if you so if you take the columns one, second, and third columns, so these were the eigenvalues and the unitary transformation that we did. So any matrices O which is not diagonal, you can do a U dagger U and you get a diagonal matrices. And the column of these U matrices are basically the mm, eigenvalues, sorry, the eigenvectors of that eigenvalue. Do you remember?
Columns of U.
Yes, so you have a matrix which is not diagonal. That means the diagonal elements and other off diagonal elements are not zero. So now if you diagonalize the matrix, so it will have eigenvalues, and for each eigenvalues there should be eigenvector corresponding to that. So
Yeah.
those eigenvectors, if you stack column wise, that gives you the unitary matrices that we have discussed in one classes, and that is actually basically your ls. So ls is the eigenvectors. So I can print it if you want to see. It will be a 7 by 7 matrices. Yes, this is the number. So if you check this line, 1, 2, 3, 4, 5, 6, 7. So it has a 7 column and 1, 2, 3, 4, 5, 6, 7. Oh, sorry. This is the matrix. So it has a 7 by 7 matrix. It is printing in a different way, but it's a 7 by 7 matrix, and each column is the eigenvector. That's why I discussed all those stuff previously. Like if you diagonalize a matrix, how will you get the diagonal elements and um, the eigenvectors? If you have forgot, that's fine. If you just check it out once, I think it will be clear. So the columns of this LS, the
Yeah.
message is the columns of this LS is basically the eigenvectors for these eigenvalues that is there in the lambdas.
So LS notation, like have you used this for any other any other notation for this term before?
In the course, I think, just let me check. They have, what is the, oh, so you want me to tell that what is the notation used in the course?
Yeah.
Okay. So just
Previously, we
give,
might also have discussed.
uh, just let me check what is the notation they have used in the course. Yes, in the course, they have used the X as the,
Oh, okay, got it.
yes, so X is the matrix that converts the non-orthogonal to the orthogonal basis. So X is the notation used in the course. Okay. Okay. Let's go forward. And now you have to calculate this lambda to the power minus half. Right. We are going step by step. And lambda to the power minus half. And how will you calculate the lambda to the power minus half? So, so I'll encourage you that you have seen the idea that I'm doing here. You don't see the code. You first from the scratch you try to write it. So the way I'm going to write it, I'll not say it's advanced, but the beginners don't write in that way. They will simply open a loop and they will fill up all the numbers. So I'll show you. But as I am quite aware of these Python codes, so that's what I'm using this. But I'll request you that you please try from the scratch. You open a loop. So the more dirty code you will write it, you will learn like then you will learn it properly, like what is the optimization and what is the thing that I can improve. So if you see my the first Hartree-Fock code that I have written, that was a, I think I don't know 300 pages. And when I wrote this code yesterday, I saw that my first code was it's a garbage, but it was giving me correct values. It was giving me the exact number that I'm going to get from this code, but this is even cleaner. But the first code that was garbage, but there I learned a lot. Like I opened the loop and I so here I'll so in this example when I'll sort this density matrix, initially I didn't know how to sort the data. Like you which is a two-line code which I am going to show you here that I wrote in I think 20 to 30 lines. So you don't see the code, you just try to write it on your own. Don't use ChatGPT and any other stuff. You just give your idea. See, I want to do it. Can we help me? That way you can ask the ChatGPT, but please don't ask. Please write a Hartree-Fock code for me. Okay. So this is just a suggestion from my end. Okay. So
Lambda is comma L is okay. So
sorry.
because eigenvalue, okay, eigenvalue is matrix.
So if you remember the Professor Pal's lecture, so if you need the s to the power minus half, right? But you cannot actually calculate the s to the power minus half from s. So that's why you diagonalize it. So you get this lambda s, and if you take the eigen, so this is a now it's a
Uh,
diagonal matrices. Now if you take the all the diagonal elements to the power minus half, and if you convert it, that will be your s to the power minus half. So that's why that's how you calculate the s to the power minus half. So I have calculated my lambda s, but I need the lambda to the power minus half.
so this is back transformation.
Yes. So
But
it's
I was only with two values for the orthogonalization matrix. Like this is
uh, two values.
oh, so basically is it two dimension is it?
I didn't get your question.
Like lambda is I was confused in the syntax actually. Like in the code,
In the code,
just
yes,
one.
I am getting the eigenvectors and the eigenvalues.
Oh, okay, that's how this function works. Okay.
So I am all like I only did this line, but now I am going to do this. I haven't done this yet. I have only diagonalized the S matrices. Now I need the lambda to the power minus half, which I am defining as lambda half. So here I am using uh, so yes, that is 1 by np dot square root np dot square root I for I in lambda s. So here what I'm doing is that, so lambda s has the eigenvalues. So for each values in the lambda s, I am taking the square root and one by of that square root, which will give me this lambda to the power minus half, and that is I'm defined as lambda half. And when you will write a initial code, you will first do a for I in range or I in lambda s. You will define a blank list here, and you will fill each the like you will fill each number, but you can write it in a single code, right? So this part is clear, right? I have defined the lambda to the power minus half. Now I need the s to the power minus half. So s half. S half is what? S half is ls times lambda to the power minus half times ls dagger. So ls, so let's write ls, and matrix multiplication I am using at the rate. So in this way you can write the matrix multiplication, but I'll show in like the different way you can write the matrix multiplication. This is one of the way. ls lambda lambda half ls ls dot t. So the ls dagger is basically um, the conjugate and transpose, but here we are only dealing with the real numbers, so that's why I'm only using the transpose here. You can also do dot conj here, there is not a problem, but yeah, for simplicity it's fine. Any doubt in this line? So
No.
I just wrote this line. Is it fine?
Yeah.
Okay, so you have defined the s to the power half. Now see the step 5, initial density. And how did they make the initial density? They have defined as a f0 dash. So f0 dash as s half dagger h core s half. So s half dagger h core. So the initial we take the h core if you remember from the lectures, and s half. So we have defined the Fock matrices here. Now you have to diagonalize the Fock matrices. Again, we'll use this to diagonalize it. So here you will pass the f0 dash here. And what is the nomenclature? They have given f0 dash and c0 dash, right? And your this is your epsilon 0. So what is your eigenvalues? Your epsilon 0, and your coefficient is c0 dash. Is it fine up to this?
Yeah.
Right. Let me see if there is any error. Yeah, there is error. Uh,
Let's see.
Zero dimensional array.
The below part of the code I've not seen actually for A in else.
Sorry.
Can you scroll below?
I see. I see the problem. Yeah.
Yes.
So the
One
problem
nine.
is
Okay.
uh, this lambda half is a matrix. So it's a sorry, it's a list still. We haven't converted into the matrices. So if I print the lambda half, you can see it's a number or it's a list, but I have to convert it to the diagonal matrices, and which I did in the previous lectures when I showed you all the. So you can this is a just one line thing. Np dot diag. Yes. Now it will form a diagonal matrices. Now if I want to print it, yes. So see now it's a diagonal. All the terms are zero, and they have put all the elements in the diagonal. Now everything is fine. Yes. So we have got the epsilon 0, C0 dash. This part is done. Now we have to transform the eigenvectors into the AO basis. I'm not going into the theory that is already discussed in the lectures. You go and check, and then you can see that all the stuffs are same here. So now you have to define the AC0, that is S half times C0 dash. So that is your X matrix that is there, that was given in your lecture. So C0 is S half and C0 dash. So S half and the rate C0 dash. Yes. And now, so there are hints are given here. So the transform Fock matrix, if you see, they have given, and you check that whether we are getting the same value or not. So let's print F0 dash. I don't know whether we'll get the same value or not. Yes, this is 32 and 403 and all. 403, 0.446. Yes, we're getting it's correct. Yes. Okay. So far, so good. Um, Let me check once. Yes. Now this part, density matrix. Is there any doubt, Diptanu?
No.
You need to live by 840, right?
Yeah, 848, 45.
Okay.
If you
I
can.
think today, so the main part. So I think it has been a long time we're discussing the coding. So let's do a overview that what we are going to do. So we'll get the density matrix. The major challenges in this project is that you need to write the iterative function. So ACF is the self-consistent field theory. So you need to iterate the thing, and that is where you need to write a. So I have written all the code here already. For example, this is the code, the SCF iteration. So here we need to spend a lot of time. Right, all the things are done. So the major struggle we have done here is the loading the matrix and then uh, like filling up all the array. We have already done it, but we have to write this SCF iteration carefully, and then we need to check the convergence. So we are checking the convergence here. That we'll do it. So I don't know that whether in this class we'll be able to finish it or not. So but I wanted to finish it today, uh, but I don't
So
know
let's
whether
see
I'll.
how much we can do.
Yeah, let's see how it goes. Otherwise, we can continue in the next class. And
850 till 850, it's fine.
okay, yeah, it's fine. And so MP2 is already been taught in the classes.
Yeah,
I
yeah.
guess so, yes. So, so in this project, you can find many other stuff interesting. So let me just quickly show you. This is project 4. Yes, this is the molar placid perturbation theory. If you have coded the Hartree-Fock, then the MP2 code will be very simple, and here you will learn a lot of things like this, how you transform the integral, and all the things are given. And in the
Okay.
project 5, I think. Uh, Couple
So,
cluster. So I have done up to this CCSD, and this is a bit advanced, this CCSD. But I will request you that if you are really interested in this, then you can actually code up to MP2 and see that whether you are getting all the correct numbers. But actually you
so
will get a
what are the previous projects on?
the previous projects are like project 1 and 2, I think, molecular geometry analysis, like reading files, bond length, bond angles, how do you calculate this stuff? Uh, you can go and check like what are the
Okay.
other stuff they are given. Yeah, I haven't done it. Like I have done only 3, 4, 5, and maybe 7 or something. So yeah, so the MP2 will be interesting. If I don't think so that I'm going to do it, but if we have time, we can show. And I think I have told you that I'll show you Orca file how we can run a MP2. So I can we can discuss something based on the result that we are getting. Maybe we can also show what is the meaning of the lines in the output file that you get in the usual software packages. But yeah, those are the other stuff. So let's finish off this part. So yes, so we have defined up to C0. Now the part is the density matrices. So before that, let me show you what is so the initial Fock matrix you are diagonalizing here, right? So this epsilon 0 is basically your initial orbital energy. So the epsilon you write, that is your epsilon 0. So, and let's see what is the epsilon 0 they are giving. And when I did the first 34 code, actually in this line, I was stuck for um, maybe 2 days that I was not being able to. What is the problem? So here you
Which
can
line?
see. So in
Okay,
this line
A0 equal to
actually,
S half. Okay, okay,
yes. So
okay.
when I'm going to form the density, I was not getting the correct density because what happens is that when you do I think I did 1 minute. Yes. So here I am using a EIGH, but if you use a EIG, which is a general, that the getting the eigenvalue, so you can see that the energy ordering here. So the energy ordering is that the first. So when you form a Hartree-Fock determinant, what you actually do is that you take the lowest energy orbitals and you form a single determinant. So you have seven energies, right? So seven MOs. So you need only five lowest. So what I was initially doing is that I was taking the first five because I was assuming that okay, my first five will be the lowest. But if you see when I use the EIG, actually you are getting it's a random energy ordering. So the first two is the lowest, but 7.55 should have come after 8.08, right? So now to sort this array, I wrote a like big function, but it can be actually done within a single line. So I'll just show you. So what you can do is that you can define a argument, or you can define a variable np dot arg sort, and you pass the array. So what it actually does is that it actually sorts the array ascending order, the lowest value first and the highest value at the last, and it gives the argument of those numbers. And now if you C epsilon 0 is equal to epsilon 0, and if you parse the argument and if you print the epsilon 0 now, you can see it is sorted.
Why are you using EIG instead, like EIGH and not
So
like not EIGH and EIG?
So, for example, if you solve a couple cluster problem, your Hamiltonian there, that is called the similarity transform Hamiltonian, that is not Hermitian. So, diagonalize that matrix, you cannot use the EIGH. So EIGH is only for Hermitian. But for the Fock matrices, we know the Fock is a Hermitian matrix. So that you can use EIGH. There is no problem. But to generalize thing, I am using EIG. It's up to you. You can. I think it is when good to use EIGH because you already know your fork is Hermitian, so you have to use EIGH, right?
So why is EIGH for Hermitian only? Like,
Yes, so
what's the
EIGH is a
difference
function they have defined in the NumPy program that
for
actually
Hermitian?
for the Hermitian. Uh, so what is uh, the good thing about Hermitian is that it's a fast process because uh, uh, when you have a Hermitian, you have the information like, for example, for any matrix AMN, so you know that what will be the elements of my ANM. So you can diagonalize the matrix in a much more reduced dimension. So it's a computational science thing, like how can you make the program faster? So for example, the
So how are the
diagonalization,
results different? Like,
uh, you
with the
start with
sorting,
the
you said it comes different. So that was
So you start with a non-Hermitian matrix, and I'll suggest that you write a matrix A, okay, and you create a NumPy array, which is just a simple matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, which is a non-Hermitian matrix because the elements they are not the same, right? So now you use EIGH to diagonalize the matrix and EIGH to diagonalize the matrix, and you check the value. It will be different, right? But if you use a Hermitian matrix, you use EIG or EIGH, that will give you the same answer. So this is just a actually EIGH is much faster than EIG, but in general people use EIG. So okay, so we can use anything you want. So we'll use EIGH for the Hermitian matrices, and we will sort the data. Now there is a problem that if you sort the epsilon 0, right? So again you have to sort the coefficient matrices because the can you tell me why you need to sort the C0 matrices? Can you answer that? Why, when I sorted the eigenvalues, why do I need to sort the coefficient also?
because they are multiplied.
Like, so see this line. Okay, so you have a Fock matrices. You diagonalize the matrix, and you get seven eigenvalues and a a 7 by 7 matrices, which each column is the eigenvectors of the eigenvalues. So initially, the first eigenvalues corresponds to the first column, second eigenvalues correspond to the second column, third eigenvalues to the third column. But when you do the sorting here, so you did the sorting here, so now you are shuffling here, right? So, for example, this 7 minus 7.55, it was appearing at the sixth places. Now it is appearing in the third places. So
Yeah.
now if you use the previously C0, so the sixth eigenvalues
So they
eigenvector
are
is the third one, which is wrong.
will be shuffled. Yeah.
Yes, so again you need to shuffle the columns in the same manner you are doing the for the eigenvalues. So this is a thing that you need to remember. Yes. So yes, we are done. Now we'll form the density matrices. Density matrices. So here I'll show you a different way of matrix multiplication. Let's say D0, the
The
initial density.
argument thing, why? Can you repeat also?
Sorry, this
Argument.
this is not clear to you?
Yeah, you said because we need to sort it because ing function. But like
Mhm.
why? Uh, like we are taking this in the writing C naught again. Yeah,
Like,
that I got. But
mhm.
okay, basically to sort them. Nothing.
Yes, this is just sorting procedure. So the sorting is that I want the lowest five eigenvalues or lowest 10 eigenvalues to my first columns or rows, and then the rest I will call them as virtual. That is the main goal. Okay. So now you have to. I'll show you a like this matrix multiplication. You can use the matrix multiplication the way I did here, but in usual the way we write is that it's called the einsum, np.einsum. It's a, a different way of solving actually higher dimensional matrices. So for example, here you can see is a mu m, right? So let's write mu m. So I am writing as k, and here it is nu m. So mu m, nu m. So mk nk, nu m. And this will give me I1 as nu mu. Or,
This I didn't get.
okay, so, okay,
Einsum is the sum of the I think all the epsilons.
yes, the sum of the, so this is basically a matrix multiplication. Let's say you have a matrices, which is a shape of, let's say, mk, and you have a matrix which is a shape of nk. And how do you do the matrix multiplication? You take mk comma km, sorry,
Mhm.
kn, which will give you mn, right?
Mhm.
So so that is the thing I am doing here only. So this is the way you can do a matrix multiplication. So so you can see here I am using the kn. So I'll show you different possibilities. So just let me
Okay.
write it. So this is
Mhm.
a another way of doing matrix multiplication, and it is the most used in the modern electronic structure codes that we use. That's amp.einsum. It's a very,
Then we should write C0 comma E epsilon 0.
yes. So here now we'll use this as the argument, c0 mu m. But please note this, where m indexes the columns of the coefficient matrix and summation includes only the occupied spatial orbitals. So now you cannot just pass the C0.
Okay.
You have to pass. So let me sketch it here. So now this C0 matrix, it's a 7 by 7 matrix, right?
Mm.
7 by 7 matrix, and you have a epsilon which has 7 values. So lowest 1, 2, 3, 4, like this, 5, 6, and 7. So these 5 was your lowest values. So here you have 1, 2, 3, 4, 5, 6, 7. 7 number of rows, 7 number of columns. Right. Now this is your occupied because in H2O you have 10 electrons, and so which is actually 5. So you have to take only 5. So you have to take only this portion of the coefficient matrix. So this is your virtual, and this is your occupied. That's what they meant. So the density you form from the occupied matrix, and that's why we need the sorting. Is it clear?
Okay. Yes.
Okay.
And regarding the M and N,
Huh?
uh,
So
yeah,
C0 mu m. So just let me write once. Then I'll so C0. Now what I need mu m. So your mu, this is your NMO. So that is whole thing that I'll write. But you need up to m. So up to occupied. So up to NO occupied. Look at this. Your C0 is a NMO comma NMO matrix. So in the columns, I need up to occupied. So I have defined the occupied here, right? NO is 5.
hmm.
So I am taking only up to occupied number of columns. But I am taking, so this is your, so this is your mu m, mu m, right? So mu has to be go from 1 to nmo. So that's why I am taking up to whole, but here I am taking up to only no. And similarly, the same thing here also, like nk. So now we
So
have
what does
found
the second index represent? The
nk.
lines of, yeah.
So the first argument that you pass here within the string, that tells you that the, so with this string, actually I am telling the code that you perform a summation over the k indices. It will sum all the k indices, and it will give you a resulting matrix which will be a shape of m by n, which I actually need here, mu nu. So INSUM is
K
not.
indices here referred to,
Mhm.
K indices referred to here.
Acha. So k here is actually your m. So I have, for the mu I have already used. So in here you cannot use mu nu. So there, so if you write, for example, mu nu, if you want to write mu and m, right? Mu, or let's say m.
Hmm.
If you write like this, actually the code will see that my matrix is a three-dimensional matrix.
Okay.
So you cannot write actually the mu, nu, those kind of stuff. You have to just use letters. So you have to use, so for mu I am using m, and for m I am using k. So I'm using m for mu, and for m I'm using k. And for nu I'm using n. So I need to get a m by n matrices, which is actually your mu nu.
Hmm.
Okay, so I got the density matrices here, and let's print it. And they have, I think, given the initial density matrices here. And let's check the value, 1.0650117. Yes, it is coming like the same, 4.26 and 4.26. And I think we're good up to this part. Okay,
Hmm.
so the density is formed. Then we can calculate the escape energy. Uh, I think I'll stop it here today In the next class, what we'll do, we'll start from here and we'll finish up this part, the
Okay.
test of convergence. I think it's been a long. I think you are also bored,
No, no, it was good.
but it's okay. So we'll
Yeah,
start from here.
yeah.
You can practice up to here, but this einsam is a very tricky thing. It's not a one-day job to learn this einsam. Um, you need to
Yeah,
get
I've
a
never
yes,
heard this function before.
but this einsam is actually so what we are developing in our lab also. We use this numpy.einsam like extensively. This is the most used function in any Python-based quantum chemistry program. So it can actually deal with any third dimensional, fourth dimensional, six dimensional matrix. So this is pretty good, but it actually
Can
requires
I
some. Mhm.
can I understand why we can't right now? Like, why can't we use any normal sum or something?
Yes, so you could have used like for example you could have used just to show you one that example you could have used C0 this matrix multiplication C0 this. But here is the catch, you could not use this because here you have to use a transpose. Then
Hmm.
otherwise it will not be your here see mk nk. But to do a matrix multiplication, the second dimension and the other dimension has to be same. So that's why you have to use a transpose here. But these two will give you same result. You can
Okay.
also use uh, d0 is equal to numpy dot there is a function like np dot there is other functions. So they are actually basically good for dealing with matmul. I'm just giving you different possibilities. They are good with your two-dimensional matrix. But for example, if you go to the if you know the T2 amplitude in your MP2 code, that is a four-dimensional thing. So they are actually even in this project when I will solve this line, this new fork. Here you can see you are dealing with a four-dimensional matrix, and you can easily write this function within a single line. So that's why
Okay.
this einsam is very good. So I'll suggest you take a look in the Google and other stuff how to use
Okay.
the einsam. Then maybe I
Okay.
think in the next class it will be even better.
Okay.
Okay. So I think we'll stop it here today, and in the next class we'll discuss the remaining part.
Okay. So, are we using Python here because a water molecule is
Yes, yes.
simple?
Water molecule and H2O3G, it will just take a fraction of second to calculate. And even for larger molecule, people use PyScape and other stuff. But yeah, most of the cases,